All right, so today we're going to talk about what's called the derivative. And the very first thing I want to do is here's a curve, right? And we have 2 points on this curve. And I'm going to draw a line connecting those, just like this. All right. And this is a secant line right now. And let's call this y equals f of x. All right, now what we're going to do is this point has an x coordinate, and we'll label that one x. And we are going to go from here, we are going to go h units to the right and pick up this point. So I'm going to go h units to the right, and then that's going to be this point right here. I'm going to go down to the x-axis. So this distance is h. So the x coordinate here would be x plus h, okay? And so the coordinates right here would be f of x plus h. I'm sorry. Oh my goodness gracious. I said that wrong, completely wrong. All right, the x coordinate is x plus h, and the y coordinate would be f of x plus h. Okay, now this is a little bit different than what we've been doing, okay? This x value right here has been a number for us up until this point. Now this x represents any x on the curve, and this x plus h represents a point to the right of this one, okay? So then this point right here would have coordinates x comma f of x. All right, so if we shrink this down to 0, right? If we shrink h down to 0, then that's going to cause this point to come along the curve because this horizontal distance is shrinking, and we get a tangent at this x value. All right, and that is the definition of what a derivative is. Now, a derivative is actually another type of function, okay? It's going to be a formula that, because this is an x, not a number, it's going to represent the slope for any x value, okay? So the derivative of the function f with respect to the variable x is the function f prime, and that's the notation we use, f prime, whose value at x is, and so f prime of x is the limit as h approaches 0. Okay, that's going to cause this to shrink and get the slope right here at this x value right here. Okay, so the limit as h approaches 0 of f of x plus h minus f of x over x plus h minus x, right? The difference between the x coordinates, we get h. So the difference between what we've been doing and what we're doing right now is there's an x right here, okay? So what's going to happen is this is going to give us some formula. It's not going to give us a number. It's going to give us something like 2x or x squared or something like that, okay? And we got to say this, provided the limit exists. So the limit would have to exist, which means the limit as h approaches 0 from the right and from the left would have to exist. Now, for right now, we're not going to have to worry about the right and the left, okay? That's coming up in the next few days, all right? So what this does for us is we don't have to keep doing these. We can do the limit once, and then if I want to know what's the slope at x equals 3, we can use the formula. What if I wanted the slope at x equals 2? Use the formula. What if I want to know the slope at x equals -5? Use the formula. I wouldn't have to do the limit every single time because this x represents any x value on the curve, not a specific one like what we've been doing, okay? All right, let's go to the next thing. So there's definition of derivative, what I just covered, and there's definition of derivative at x equals a. Now, this is a specific value. So this is exactly like what we've been doing. The only difference is now we have a little notation for this. So f prime of 2 or f prime of 5 or f prime of -3, okay? And so right here, this a right here represents where I'm going to find the slope at, and it's really just the same thing, okay, as what we've been doing. Now, when we do this, okay, this is going to come out to be some number. So there's a difference between these. This is going to be a formula with x, and this is going to be a number value, because this is the slope at this specific a value, okay? And so this is the notation that from now on, you're going to see me using this notation, f prime of a, okay, or f prime of 3 instead of f, and that would be the derivative of the function f at a. Once again, I'm going to draw a line through these 2 points. And this, because it's 2 points, it's the slope, right? We can find the slope between these 2 points. All right. And what I want is I want the slope at exactly this value right here. Okay. And this value is I'm going to call that a. I'm still going to call this y equals f of x. All right. And then this point right here would have coordinates a comma f of a. And now what I'm going to do is I'm going to pick another coordinate, and I'm going to call it x, and it's going to be over here. And I'm just going to call that x. And then this point right here would be x comma f of x. And this is just another alternative way of saying the derivative at a point, okay? So now let's talk about what this means, okay? The derivative of the function f at the point x equal a is the limit, so it has to be a limit. And this is what the slope's going to be at a. It's going to be equal to the limit as x approaches a. So what happens as x approaches a? Well, as x approaches a, that means this is going to have to move and get closer and closer and closer and closer to this a value, right? Which is another way of taking this point and moving it along the curve and getting it closer and closer and closer, okay? So now the secant slope between these, remember, is this secant slope is f of x minus f of a, the difference between the y coordinates, over x minus a. And that's where this comes in, okay? Now, this is the slope between 2 points. This is the slope between 2 points. This is a slope at 1 point, and it's because of the limit right here, okay? The limit as x approaches a. So it doesn't approach 0, it approaches a, where we want to find the derivative at. And I'm going to have you do the derivative at a point both ways, okay? You got to do it. You got to be able to do it both ways and understand both of these formulas, okay? All right? And I should have said this, okay? The derivative, I said it, but I didn't write it. The derivative gives us a formula for calculating the tangent slope at any x value. Okay, that's different than what we just did up here. This is the derivative at a point. This is going to be a number value. Okay, so I'm going to say equal, this is going to equal some number value. So this doesn't give us the derivative, it gives us the derivative at a point. Notice it's different. It doesn't give us the derivative, it gives us the derivative at a point, okay? So the derivative is the one that gives us a formula, okay? So we're gonna call functions different names, and I'm gonna show you some different notation that you're gonna see. So if you see f of x, you've already seen this notation for the derivative, and it would be f prime of x. Sometimes you're going to see y, and the derivative would be y prime. Okay, so we use these primes to do it, to show the derivative. Okay. These next two is going to make more sense as we go along in the class, okay? Another way of writing y, the derivative of y, is dy over dx. Okay, this is, remember, it's slope. So this is it comes from delta y over delta x, okay? So we say for this, the derivative of y, when we read this, we say the derivative of y with respect to x, okay? So that's another way of writing the derivative. So dy over dx. This notation isn't going to completely make sense at first, okay? Another one is this. If we have a function g of x, sometimes you're going to see it like this: d dx of g of x. And it looks like that. Sometimes this is useful. All these have their place, okay? So this is an alternative form of this, because remember y? Y is the output. Well, g of x is the output too. So this is kind of an alternative form of this. You could think of it as being like this: d, the derivative of g of x with respect to x, okay? And so we put a bracket on here when we're saying we're taking the derivative with respect to x. We are going to take the derivative with respect to other variables. That's later on, so don't worry about that. But that's why I'm saying with respect to, okay, what the independent variable is, which is x here. All right, let's do some problems now. So for this, we're going to use the definition f prime of a is equal to the limit as h approaches 0. So here's my point. It's going to be at a, and my second point is going to be a plus h, so it's going to be to the right, okay? And my a in this case is going to be 3, and my function is 1 over x plus 5. So I did one very similar to this one yesterday with you guys, okay? So we want to find, now we can start using this notation. So it's at a equals 3, so we're actually finding f prime of 3, and that's the derivative at 3. So it's not the derivative, it's the derivative at 3, which is different, okay? So this is equal to, all right, the limit as h approaches 0 of f of 3 plus h. That's 3, and I'm going to the right, h units, and then minus f of 3 all over h, okay? So then this becomes the limit as h approaches 0 of, and since my function is 1 over x plus 5, this is going to be 1 over 3 plus h plus 5. And then minus 1 over 3 plus 5, so that'd be 1/8 all over h. And this cleans up a little bit, so this is equal to the limit as h approaches 0 of 1 over h plus 8 minus 1 over 8 over h. So we've got a complex fraction like we did yesterday, and so we want to multiply by 8 and also h plus 8. Okay, so we're going to need to distribute this because we have a difference between these two fractions right here. So I'm going to need to distribute this with each of these fractions. So this is equivalent. We got to keep writing the limit. So the limit as h approaches 0 of, and here my h plus 8s are going to cancel. So I'm going to be left with 8 minus, and here my 8s are going to cancel, and I must write h plus 8 in parentheses over, and this is h times 8 or 8h, 8h times this h plus 8. Clean this up a little bit. This becomes the limit as h approaches 0 of 8 minus h minus 8 over 8h times h plus 8. This becomes the limit as h approaches 0 of negative h over 8 times h times the quantity h plus 8. Here my h's are going to cancel, and so I'm left with the limit as h approaches 0 of negative 1 over 8 times h plus 8. And now if I put 0 in here for h, this is going to be 8 right here. Multiplied by 8 is 64. So the answer to this is negative 1/64. That is, now that is the derivative at x equals 3. Okay, so that's the derivative at 3. That's not the derivative. It's the derivative at. Notice I'm saying at this particular value, okay? All right? Don't worry, it's coming where we're going to find the derivative, the formula, okay? It's actually example number 3. Okay, let's do this next example using the alternative form of the derivative at a point. All right, for this one, we want to use the definition that f prime of a could also equal the limit as x approaches a of f of x minus f of a. So here we are at this point a, and the x, this is going to be an x to the right of a. You can think of it as actually being either side, but I'm going to think of it as being to the right. All right, and we're going to subtract these, and we're going to make the x get closer and closer to a, which would make the point on the right go right on top of the point at a. And I hope you can visualize that, okay? So we're finding f prime of 2, and our function is the square root of x plus 3. We haven't had one of these in a while, okay? So this is going to be f prime of 2 is equal to the limit as x approaches 2 of f of x minus f of 2 all over x minus 2. Okay, that's the slope between the point at 2 and the point at x. And if we make the limit as x approaches 2, then what's going to cause is that point is going to be on top of the other point, right? And look, what if we try to do direct substitution right now? We get f of 2 minus f of 2. That's 0. We get 2 minus 2 in the denominator. That's also 0. See how we're still getting 0 over 0, okay? So this is equivalent to the limit as x approaches 2 of f of x, which is just the square root of x plus 3, minus the square root of, and we're going to put 2 in here for x, so that'd be 2 plus 3, so that'd be the square root of 5, all over x minus 2. Okay, so you haven't had a problem like this in a while, but if you try to do direct substitution, you're going to get the square root of 5 here minus the square root of 5 here. That's 0. And then the denominator 2 minus 2, that's also 0. Okay, so how can you change this algebraically? Well, you can multiply by the conjugate of this numerator. As long as you multiply the top and the bottom by that, we're going to be able to clean this up. Okay, so what we're going to multiply by is the square root of x plus 3 plus the square root of 5 over the square root of x plus 3 plus the square root of 5. And this sets up a difference of squares, which is going to cause us to square both these, okay? All right, so then this is going to equal, I'm going to travel over here to on the left. This is still equal to the limit as x is approaching 2, not h, but x is approaching 2. Okay, so if you multiply this out, all right, you're going to get square root of x plus 3 times the square root of x plus 3, which would just be the square root of x plus 3 squared, or x plus 3. And here you're going to get positive square root of 5 times the square root of x plus 3. But here you're going to get negative square root of 5 times the square root of x plus 3. They're going to cancel each other out. Hopefully you can see that. Okay, and then you're going to be left with negative square root of 5 times positive square root of 5. So that's negative square root of 25, which is 5. So we're going to subtract 5 over, and then here we're not going to want to multiply this out. Okay, we're going to have x minus 2, that quantity right there, times this quantity. So times the square root of x plus 3 plus the square root of 5. You guys, I'm realizing maybe you didn't know how I multiplied this to get here. So let me go back and let me just do this really quick with you. Okay, so it's a 2 by 2. In case you need this, okay, the square root of x plus 3 minus the square root of 5. And then this one's going to be the square root of x plus 3 plus the square root of 5. And this would be the square root of x plus 3 times the square root of x plus 3. That's just x plus 3. This one becomes negative square root of 5 times the square root of x plus 3. This one here becomes positive square root of 5 times the square root of x plus 3. And this becomes negative square root of 25, which would just be negative 5. And that's where I get the minus 5 right there. Okay, so now this becomes the limit as x approaches 2 of x minus 2 over x minus 2 times the square root of x plus 3 plus the square root of 5. And if you think of this quantity as a whole, like x minus 2 as one group, it's going to cancel with this one, right? And you can think of this as being multiplied by 1, and then these cancel, and you're going to be left with a 1 on top. Okay, so this is equal to the limit as x approaches 2 of 1 over the square root of x plus 3 plus the square root of 5. Now, can we do direct substitution? And the answer is yes, because it's not going to make the denominator be 0. So this is going to be 2 plus 3, so that's 5. So this is the square root of 5. So this becomes 1 over the square root of 5 plus the square root of 5. Okay, we got to clean this up. This is a good answer, but it's not the best answer. This is 1 over 2 square roots of 5. Okay, and now we don't want to leave square roots in the denominator, so we're going to multiply by the square root of 5 over the square root of 5. And this becomes the square root of 5 on top over 2 square roots of 5 times the square root of 5. That'd be 2 times the square root of 25, or that's going to become 5, or this becomes the square root of 5 over 10. And that's the slope at x equals 2 for this function, the square root of x plus 3. That's the slope at x equals 2. So this is the derivative of the function at x equals 2, okay? Or f prime of 2. You could say it that way too. All right, let's do some actual derivatives where you actually come up with a rule now. Okay, so here we go. If y equals 2x plus 3, find dy over dx. Now, dy over dx is actually the derivative. It's going to be a formula, okay? And this is actually going to wind up being a very simple problem, okay? And you're going to see the connection in just a little bit. This is a straight line and with a slope of 2, right? It's a line with a slope of 2. So what's the derivative of this function? So what's the slope for every x value along this curve? Well, we can do dy over dx. So dy over dx is equal to, and I'm gonna use function notation just to kind of help us out. Okay, I'm gonna call this y. I'm gonna call it f of x. So f of x is equal to 2x plus 3. So dy over dx is the same as saying f prime of x. I just wanted to get this notation in so you start to see it and use it. Okay, so this is the limit as h approaches 0 of f of x plus h minus f of x. So this x represents all x values on the curve, right? And this one's got a little bit to the right. And then this h approaching 0 is going to make that distance, that h distance, shrink to 0, which is going to cause this point to move on top of this one, okay, over h. Okay, so this becomes the limit as h approaches 0 of, and this would be, I'm going to use a bracket here. I'm going to put x plus h in here. So this would be 2 times x plus h plus the 3 minus f of x, which is 2x plus 3, all over h. Okay, so dy over dx is equal to the limit as h approaches 0, and this becomes 2x plus 2h plus 3. And this becomes minus 2x minus 3 all over h. Okay, and then this is equal to the limit as h approaches 0. And here my 2x minus 2x, those cancel. The 3 and the negative minus 3, those cancel. And all you're left with is 2h over h. And your h's cancel here, so you're left with the limit as h approaches 0 of the number 2. Well, there's no h to put it in, right? So that means this comes out to be 2. That means dy over dx is equal to 2. Now, Mr. Mitchell, you said we weren't going to get a number value. You were going to get a formula. Yeah, this is a formula. This is a formula for the slope, for the tangent slope for any point on this curve, right? And so what this is telling me is the formula is the number is always 2. The slope is always 2. What? Why would the slope always be 2? Because this line right here, it's a straight line. Every tangent is going to land on top of the line, right? It's a straight line. It's not curving, right? So the slope isn't going to change. The slope is always 2. That's why the derivative always comes out to be 2. Okay, so what's the slope? What's the slope of the line? The slope of the tangent at x equals 7 for 2x plus 3? It's 2. What's the slope at x equals negative 5 for y equals 2x plus 3? It's 2. The slope is always 2. It's not changing. Okay, and that's why this comes out to be a constant. Okay, it actually is a formula. Okay, let's do this one. Okay, this is very similar to the one we just did. Okay, and then we'll be done. So right now, this notation right here says take the derivative of this function with respect to x. That's what I want you to get out of this. Okay, so we're gonna let f of x equal x squared plus 6. All right, so now what does this equal? So d dx of x squared plus 6. All right, so this is going to be the limit as h approaches 0 of f of x plus h minus f of x. Once again, I can't say this enough. This is not a specific x value. It represents all x values on this curve, okay, over h. This one's not going to come out to be a constant because, okay, think about this. What shape is this? This is a parabola, right? So it's curved. So that means the slope is not always going to be the same. So we're not going to get a constant like we did in example 3. Okay, I want to make that clear. All right, so now we're going to plug in this x plus h into our function. So this is equivalent to the limit as h approaches 0 of, and I would use brackets here. Okay, this is going to be x plus h squared plus the 6. That's putting x plus h into our function. And then minus, our function is just x squared plus 6. All over h. Remember, you got to keep writing the limit here, okay? This is equivalent to the limit as h approaches 0 of, okay, so when we square this out, you could do a little area model here. It's x plus h by x plus h. They're identical this time because we're squaring it. So this is x squared, this is hx, this is hx, and this is h squared. So squaring this, we get x squared plus 2hx plus h squared plus the 6 minus, and then x squared plus 6 all over h. And so this is equivalent to the limit as h approaches 0. And this is x squared. There's nothing we can do to clean this up anymore. So x squared plus 2hx plus h squared plus 6 minus x squared minus 6 all over h. And some things are going to cancel out. This x squared cancels with this x squared. And this plus 6 cancels with this minus 6, right? And so we're left with the limit as h approaches 0 of 2hx plus h squared that 6 is gone with that one, and this minus x squared cancels with that x squared again over h. We can factor an h out. So this is the limit as h approaches 0 of h times 2x plus h over h. Our h's cancel, and we're left with the limit as h approaches 0 of 2x plus h. And as h goes to 0, this is going to go to 0, which means we're going to be left with 2x. There's our formula. Okay, so this winds up being equal to 2x. So what does this tell you? This tells you that whatever x value you have and you want to find the tangent slope, the slope is always going to be double whatever the x value is. So let's say you want to find the slope of x squared plus 6, and you want to find the slope at 6, at x equals 6. That means the slope would be 12. That's what this tells you, okay? What is the slope at x equals 7? Well, it'd be 2 times 7. That'd be 14, all right? What if I wanted that -3? Well, that'd be 2 times -3. That'd be -6. So the slope at x equals -3 is -6, okay? All right, so there's power in this, and this is actually going to tell us other things later on, okay? So this is a really, really big deal. And I'm going to tell you this too. There is going to be some shortcuts to this coming up. So if you talk to older brothers, sisters, and they say, oh, why is he showing you that? It's because this is the foundation of it all. All of these come from limits. Yes. Are there going to be rules that you need to know? Yes. Okay. And is going to simplify this and make it a lot faster process. Yes. Because we can kind of generalize some of these rules. Okay. All right, guys, that's it for today. So derivative day 1, okay? Basically the whole semester, first semester, is all about derivatives, okay? That's what we're going to be dealing with the rest of the semester, is these things called derivatives. But pretty soon we're going to get away from the limits, okay? And there's going to be a faster way to do it. I'll be honest with you, there is, okay? All right, you guys have a wonderful, great day. Bye.